Hello, everyone. I feel like a rock star. I mean, they have a backstage with a super big bathroom with shower for people that are singing. I'm all mic'd up. I mean, I really feel like singing and dancing. But we're not here for that, and that's probably best for you. No, I'm sorry. I'm sorry. Those days are gone. Anyway, so I'm the only thing that stands between you and lunch, so let's make it tidy and short, hopefully. So I'm Andrea Barisani. I'm the founder of a company called InversePuff, and I'm here to present about our little project called the USB Armory. So how many of you don't know anything about the USB Armory? Raise your hand. Okay, so I hope that this will be interesting for you, and for the other half, I still hope it will be interesting for you, and I can give you more insights into our project. So just to tell you a little bit of background about what we do, so we're a company that's been doing software as well as hardware security for more than 10 years. We specialize in exotic sectors such as automotive avionics, and every 2 years we try to do a public research where we present some exotic stuff. In 2007, we were one of the first ones to present a talk about car hacking with injecting traffic information signals on a car. 2 years after that, we did a Tempest attack, sniffing keystroke using either lasers or on the power line. In 2011, we broke chip and pin. In 2014, we did packeting packet over Ethernet attacks. And then in 2015, we decided that we wanted to build something for a change rather than break the things that we were being handed to. And so we decided to build a hardware project called the USB Armory, which is this device over here, which, as you can see, it's very, very, very tiny. So what is the USB Armory and why did we decide to do it? So it's a device which is designed for personal security applications. And the main idea, the first idea which prompted the creation of such a device was to simply have secure encrypted storage with something that we could trust and that we could control. I mean, you can get a lot of USB drives which have military-grade encryption, whatever that means, and you have no idea what they do, and hopefully you would think that they would implement good security, but every time we test the hardware of those things, they're very vulnerable to trivial hardware attacks. So we wanted a device which would present itself as an enhanced mass storage, and then we could just copy a file to it, and it would encrypt the file with either GPG or whatever algorithm which we would deem acceptable and that the user would feel safe about it. But then we thought, why using mass storage? Why don't we make a device which is TCP/IP connected so that we can expose a more rich functionality to the host rather than a simple mass storage device, rather than a simple USB drive? With TCP/IP, we could just have a web server, and we could have a richer interface to do more actions for encrypting the files and also sharing the files and maybe scanning the files for malware or whatever on the device, on the USB device itself, so not on the host. And then we thought, but if we have TCP/IP connectivity, then we could also do things like having the device authenticating the host, and then maybe having the device doing data self-destruction if we don't do a certain action, if we don't present a valid certificate, or if we trigger a fail-safe word for some reason. We're thinking about expanding with more and more and more functionality. And then we thought that if we put a standard computer rather than having a single-purpose device on such a USB device, then we could also have an SSH proxy. So if I want to connect to whatever service I have, I can hold the keys on the device itself, I can SSH to the device itself with some disposable password, and then I can SSH out of the device itself to the internet. So slowly and slowly, and we can have a password manager and so on. So slowly and slowly, the idea came that rather than having a single-purpose device, there would be a great security benefit in having a generic purpose device in such a compact form factor, because it would enable not only a single application, so it wouldn't just be an authentication token or a wallet or an SSH proxy. It could be more and more applications into one device. And if we would allow to have a familiar development environment and a standard environment on the device that the user and developers could develop on, we could enable advanced functionalities such as this one, like the USB device that authenticate the host or data self-destructs and so on, which were features that you couldn't have on such a small device. at the time. So the design goals were set very clearly. It must be a compact USB power device, so something that you can carry in your pocket. It must have fast CPU and a generous amount of RAM to enable all the richer applications that we wanted to. It must support secure boot so that you can ensure that only the code that is signed by you gets executed on the device. It must provide standard connectivity means over USB, so not too many complex drivers required. And very important, you must have a familiar developing and execution environment. So not something which requires a high learning curve to develop on. And the design should be open. So we built this device selecting a Freescale IMX53 system on a chip, which is fairly powerful given the size of the device. This device is more powerful than the first Raspberry Pi, for instance. It's an ARM Cortex-A8, which can be clocked between 800 megahertz and 1.2 gigahertz. Almost all datasheets are public, and there's no NDA required, which is a very good thing. The datasheets are okay, far better than any other vendors. The device has TrustZone and secure boot, secure storage, and secure RAM support, and there's excellent native support for this system on a chip. And there's good stock and production support guarantee. So you don't want to commit to a design and then you realize, oh, now I want to make 3,000 of these, and sorry, we don't have enough system on chips in the world for having your device being built. So that would suck. So that was also one of the requirements. So the trust and support of this device. So this system on a chip is much more complex than what it needs to be for the sake of this specific device. So what we do in our design, there's a lot of things that we just don't power on in order to keep power consumption at minimum and only focus on the interface that we care about, which is mainly USB and then some other peripheral connections that we have. Trust and support for this system on a chip has a fairly good implementation. We tested a lot of trust and implementation, and we found this one to be fully adequate for being used. So what trusted is, if you don't know about it, think about it like kind of like virtualization, but it's a much simpler scheme, which only allows you to have 2 domains running in your execution context. And these domains are handled at a very low level by the CPU and the hardware peripherals. And what this allows you to do is to have a non-secure domain where you can have your user mode applications and your kernel, and then you can have a completely separate context, which is called a secure domain, when you have a separate user mode and a separate privilege mode. But the idea of Truston is that you can also use it as a hardware firewall. So you can decide to assign a specific hardware subcomponent of the system on a chip only to the secure mode. And this allows you to segregate, let's say, the microSD interface or the USB interface only to a trusted driver that you put in secure mode. And you can define a very clear set of APIs, very minimal and very restricted to the task for exchanging data between the non-secure and the secure world. So this system on a chip has the capability of assigning each hardware peripheral that's embedded in the system on a chip to only one of the 2 domains. So for instance, you can have the LED, which is present on the device, only confined to the secure domain, which means that you can do things like, if the LED turns on, you know by definition that the secure code is running at that very moment. And then maybe you can ask for a password or something like that, making sure that the non-secure domain is not phishing for that password. And at the time, there was a lack of a good playground environment and a research and training environment for Truston, and this was also one of the drivers for developing this board with this specific system on a chip. The project is completely open source. It's as open source as it gets. The full software is open source, and also the hardware, the schematics, the PCB layout, everything is open source and has been done also with an open source tool. So anyone can open the design files, can easily modify the design files without requiring any license, and it can also send the output of the fabrication output of the tool to a factory, and if you make 100 of these, it gets economical to do so yourself as well. It is very tiny. We have a microSD card slot where all the codes come from. There's no persistence on the device except for a few fuses, which I'm going to talk about. We have a 5-pin breakout header where you can attach SPI, I2C, GPIO, and serial port, and so on. And we have this LED, which can also be used for secure mode detection. We're now supported, we have official support for Debian, Ubuntu, Arch Linux, and also, if you want to play with Trustzone, there's a very nice project called GNodeOS, which implements domain separation on the USB armory, and allows you to have a microkernel into the secure domain, handling drivers such as the microSD card, and then you can boot a Linux system in the non-secure domain. So kind of virtualizing it, but not really, with this domain separation that I mentioned. And with this device, we can emulate arbitrary USB devices. We can emulate an Ethernet device, a mass storage device, a keyboard, whatever you like, and I'm going to talk about this. So, of course, the primary use of this device is device mode, as just mentioned. But it turns out that we can also use it in host mode. So we can invert the role of the device, because the USB controller allows us to have a great freedom in configuring it. And so we can have, so this is an example of the device running in host mode. This was actually one of our first tests. So we just change with a breadboard, very crudely, we change the gender of the plug, and then we attach a USB hub with a mouse, a keyboard, a USB display, and also a Wi-Fi chip, and we would just have the device running standalone, with X Windows and just using it. So we made this in a much prettier form factor. So now we also have this host adapter, which merely changes the gender of the USB ports. You feed power back in, and then you can attach. So here we have a Wi-Fi dongle, but you can attach whatever you want. So it can also work as a standalone device. And we realized this only after building the device, but it was a nice thing. It was a nice feature because the USB controller really allows you to do whatever you like. So I have some pictures for the development process. So this was a development board that we made for accessing the BGA chip. So BGA means that you have a ball grid array. So you have this matrix of little balls that it's very difficult to solder and desolder on your own. You can do it, but it's a messy process and prone to errors. And we thought that for prototyping the device, we could just get this very expensive socket that would allow us to have a solderless connection with the BGA, and then we would break out each ball and develop on this thing. But the problem was that the power regulatory tolerance requirements are so tight that you really need to put all of the power components on a proper PCB and with the proper distances. You cannot solder this on your own. And also the system on a chip needs to be on a PCB as well. So if you put the power on a PCB and the sock on a PCB, you might also as well put a USB plug, the micro SD, and then you have the final board. So at the end, this effort was kind of useless, and I was like being like Darth Vader, telling to my colleagues, you failed me for the last time, because they tried for 10 times to build a power-up that would power the device externally, but at the end we said, okay, let's just build this thing and let's hope that it works. So this was kind of like a superstar destroyer, a big thing which costs a lot, but at the end it just crashes down, it's useless. But it's pretty. So this is the layout of the board. This is KiCad or KiCad, depending how you pronounce it, the open source software which we use for the layout. The biggest problem here was to route the RAM memory to the sock, because when you route memory to a CPU, all of these traces, they need to be exactly of the same length, to the decimal point of the millimeter. And this open source tool doesn't really help you in doing that, unlike professional tools. So all of these were length match with much love and by hand, which was a very painful process. But this is the price you pay for having everything open source. On the other hand, the 3D graphics capability of KiCad are excellent. I mean, they're useless, but if you want to see your board in 3D before having it produced, you can do so. So that was cool. So this is the alpha board that we made, the very first one. It is, of course, bigger than the final product because we wanted to have a JTAG header easily accessible to understand if the board would not boot up what the problem was. And we made it so that we could also cut the excess PCB compared to the original form factor, so that then we could also test the original form factor, even if wouldn't make much of a difference, but maybe for heat dissipation, it could mean a difference. So it was designed in that way. So this is an Amontech JTAG controller attached to the device. Luckily, the device booted at the very first version, it booted up. So this actually wasn't necessary, but it was a precaution that we needed to take. And I think it's pretty amazing that with completely open source technology, we can build such a standalone USB connected computer, which is more powerful than a Pentium 2. But Darth Vader prefers this because it's black. So for this reason, we made it black and not green. So these were the different revisions. This was the alpha board. Then we made a beta. Actually, we made more than one beta. So what we decided to do to optimize the design and cut the cost of building the device, when you build PCBs, you generally have a sheet where you can fit in one tooling, in one manufacturing process, more than one revision of the board. And we could do, I think, 6 or 8 of them. So with just one production, we tested different beta revisions, where we tried to power up the RAM in different ways. By converting the 5 volts directly with the voltage required for the RAM, or by using a buck converter, by using a different power regulator in order to try and cut down the cost. Eventually, we found what was the best compromise between price and performance, and then the final Mark I design was selected from one of these. We also tried to change the number of layers. Originally, the board was 8 layers, and we were able to drop to 6 layers by, just keeping certain recommendations that they give to you, but sometimes they just work. You gotta try it. So when you make a device which is this small, you cannot be conservative in the terms of the recommendation and guidelines that the part vendors tell to you. So we did a lot of things that were not by the book, but that in the end, they worked just fine. So let me talk about secure boot, because it's an important feature of this board. And when testing, so we do a lot of hardware testing, and secure boot is often an overlooked feature which eventually allows jailbreaking of a device, because it's either not correctly implemented or because it's not implemented at all because of its difficulty. So this specific system on a chip supports something called high assurance boot, which is the Freescale NXP terminology for secure boot. And the idea is that you fuse your own keys. So we're not talking about secure boot such as the one on a PC where you might have an OEM key from Microsoft. Here, the only content is content that you flash on the device. So you fuse 4 public keys into the system on a chip. And this is a one-time permanent irreversible operation. And once that is done and secure boot is activated, the system on a chip will refuse to boot any bootloader which is not signed with one of those keys. And you can revoke up to 3 keys out of 4 if you want to. This also makes for some interesting scenarios where you can have 3 valid keys, the 4th one is junk, and then if you revoke all of the 3 keys, the device, it becomes a brick because it can never boot any code because the 4th key is random. So you can do things like that. And this, unlike a modern PC, this feature cannot be reset. So once you do it, it's done. Instead, in a PC with a password, you can go into the BIOS and remove the secure boot functionality. So this is a feature of this device, not a bug. So you have certain parameters in the register of the system on a chip, which over I2C, so these are the commands that you can invoke from the bootloader, you can fuse the hashes of the public keys that you want to, and then you can enable and lock them. In order then to sign an image for secure boot, for this high assurance boot, there's a tool from Freescale now NXP called the code signing tool, which, however, had several issues. So first of all, it's closed source and under end user license agreement. The end user license agreement is not a bad one because it actually would allow resellers such as us or people that integrate the system on a chip to also distribute the tool to its users. So it's not, I mean, it's restrictive, but it also allows a lot of freedom. But saying that the tool is ugly is a severe understatement. The tool is fairly horrible. And also, the latest version of the tool, which is the only one that now can be downloaded, breaks compatibility with this specific system on a chip due to a trivial bug which we identified, but after more than 8 months and several inquiries at all support levels, they didn't fix the issue, and they don't allow download of the previous version, which, kind of sucks. So this is a problem when you're a very, very small player in the hardware market. It's not that you don't get support from the vendor, it's that the support is kind of offensive. I mean, they tell you that they're going to look into something, and then it's really a process that goes nowhere, and you waste a lot of time. So we decided to just re-implement the tool as open source software, which was the right thing to do. So now the IMX53, the secure boot feature, can be completely used, and code can be signed for it with completely open source tools. And this, of course, applies to any board that uses this system on a chip, not specifically to this one. And we have two guides. One where you can still, we still have instructions for using the NXP tool, and we have the same guide converted also for the open source tool, so that you can compare the two and you can decide which one to use. So this was also, this was a considerable effort on our part, and we were very pleased with the results, because in the end, we make it easy to use this kind of functionality. And we often see in all of the hardware designs that we test for our customers is that sometimes features such as secure boot are not used at all, because the tools or the support or the lack of support given to the vendor to customers doesn't really allow you to use these functionalities with confidence. Also because if you make a mistake, or if you don't have a full control and overview of the process, you risk ending up with a lot of bricks, which of course when you manufacture or mass manufacture an electronic device is not something that you want. So there was a lot of engineering to make this procedure reliable and fairly easy to use. And also by open sourcing the tools, it's also very clear to anybody that uses the tools exactly what goes on in the process of signing the images and fusing the key hashes into the system on a chip. And we also make it easy to create these certificates which are required for this process. So, and the idea with this functionality is that, so the system on a chip verifies the bootloader. So this is called secure boot. And then to further maintain the chain of trust, the bootloader, which in our case is U-boot, verifies the kernel image. And that's called verified boot. So U-boot supports embedding a key into his binary blob, the resulting compiled binary blob, and this key can be then used to verify the kernel. So the chain of trust is maintained. We fuse a key into the system on a chip. We embed a key in the image, in the U-boot image. The U-boot image is verified by the system on a chip, and the Linux kernel is verified by the bootloader. So we fully maintain the chain of trust from the very moment the device powers up until the end. Now, of course, in the system on a chip, there is an embedded binary blob which performs this operation. And one of the issues that is always raised is that you cannot inspect or read this binary blob. You don't know what's the microcode which is inside the system on a chip. On this specific system on a chip, this binary blob is memory mapped. So unlike other chips, it can be freely read by memory. And there's also one effort of some people that reverse engineer to understand if there's anything funny going on. So of course, it is not open source. I mean, I challenge you to find any system on a chip that would give you sources for the microcode, but at least we can read it in this case, which was a nice feature. It's much better than just not being able to access that code at all. So it's a nice feature of that. So in our documentation page, we do have hashes for this binary blob, so you can also verify that when you receive your device, you get the same revision, the same binary blob in the system on a chip. And if you like reverse engineering, it can be inspected, and it's not long, so you can understand what it does for ensuring that the operation of this boot up process. So this is an example of a successfully signed U-boot image. You got secure boot enabled, no events, and this is an example of a fail attempt where we have high assurance boot failures. Now, this is done in verification mode, which means you put the device in a state where secure boot is not truly enforced, because otherwise you wouldn't see any debugging output. When secure boot fails, of course, you will not see the U-boot code at all, because the system on a chip will refuse to boot the bootloader. So this screenshot here is done in verification mode, which is an intermediate step which allows you to verify that you're able to sign images, that your fusing was correct, and then you can lock down the device as a last step. And this is verified boot. So verified boot, comes from U-boot, from the bootloader, which just verifies the fit image. That's the terminology for the image that it boots, which contains the kernel and the so-called device tree, which is an external file which is parsed by the bootloader and the kernel to configure the hardware of the device. So if you want to assign a GPIO to an LED or change configuration of certain pads, that's what you do into the device tree. So when we set the device in host mode, that's where that configuration is, into the device tree file. Okay, so these cover the hardware of the device as much as we could, and the software which enables you to use the hardware functionality. But then, of course, we also needed an application to show the potential for this device, the potential use for the device, and to unleash the functionalities and the use case scenarios that we wanted to. So for this reason, we developed an application which is called Interlock, all uppercase to as a reference to the NSA code names for internal projects. That's why Interlock is always referred to all uppercase. So Interlock is an open source file encryption front end, which is developed for the USB armory, but is not limited to being used on the USB armory. If you have a Raspberry Pi or whatever other ARM board, or even on your laptop, you can use Interlock freely. There is nothing specific in Interlock, no code which is specific for the USB armory. And this project provides a web-accessible file manager, which is tied to the Linux Unified Key System framework for encrypting and decrypting partitions. And also, we implemented additional encryption features on stored files. We take advantage of disposable passwords and unique options of the Linux Unified Key System to have more than one password. And I'm gonna show you a demo of this application. So first of all, here, let's see if you see it. Maybe I can set the font a little larger. Text. Looks. No, okay, anyway, it's not that important. I just want to show you that here I'm in Windows because I'm presenting a presentation to you, and the biggest problem in IT nowadays is presenting from a Linux OS, which is why we use Windows for this. But if I feel uncomfortable for whatever reason and I want to jump into a Linux environment, here I just SSH into my USB device where I feel warm and fuzzy that I have this real Linux environment running and not a virtualized one. So as you can see, it's very responsive. It's just, connected to my Windows machine. It just acts as a standard Linux box with half a gigabyte of RAM available. So simple. So now, this is the Interlock application. So I plug the device into my laptop. Windows assigns, or actually, the USB device assigns an IP address to Windows, because if you have a DHCP server running on the USB device, the Windows OS will ask for an IP address to the device, which also enables some offensive usage, which I'm going to mention later. But the first thing that happens is that when I connect, the Interlock server asks for a client certificate. If I don't have a valid client certificate in my browser, then I can never talk to this service, which is also, a very nice feature. As soon as I pass this step, I get prompted with a volume name and a password. Now, these passwords can also be disposed of after use. So I can have more than one password associated to my encrypted volume. So if I'm using this device on a computer which I don't fully trust, and I don't want loss of the device to cause compromise of the encrypted contents because someone might have sniffed this password, I can just tick that box, and as soon as this password is being used for unlocking the contents, it is wiped, so it's not valid anymore. And of course, you can have more than one password in the system. So this is a feature which is provided by the Linux Unified Key System. So now, these credentials are the credentials which unlock the encrypted partition. We don't have an external database. We don't have a password file. So as soon as I log in, those credentials unlock the encrypted partition. And this is what this interface that we have is showing to me. So it's a sort of kind of Google Drive interface where I can see my files. So let's say that I want to upload a file to it. It is as easy as just dragging and dropping the files here, and the file now has been uploaded onto the encrypted partition. Every file that you see here is encrypted. It stays on the encrypted partition. And once the file is on the encrypted partition, I can also decide to encrypt it with either a symmetric cipher, AES, or with OpenPGP, for instance. So now I've encrypted this file with PGP. All of these operations are running on the USB armory itself. And there are no external dependencies for doing this. So we don't pipe to the GPG binary. All of this is done by using standard Go libraries. This is a Go application, which makes it, I would argue, more auditable. And it's also nice because we get one single static binary without any external dependencies. So the environment for running interlock can be very, very minimal. I can view files from this interface. Of course, I can download a file. I can also download a directory. It will just be compressed and given to me. Or I can compress the directory. I can encrypt the directory and just download it, making sure that no clear text content get downloaded to the host. We have a full log here of what's going on, which also store on the device. We can generate a GPG key. We can import a key if we want to. And we also have functionality for one-time TOTP keys, so the Google Authenticator keys that you use. So this is the key for my GitHub, like the second factor authentication, and you can refresh it and so on. So you can also have a backup of those here. So on top of these features, we also added integration with Signal for messaging. So this device now has an associated number which you can register by using this function. So you can register a number either via SMS or voice. So have a SIM or have a number, it could be my landline or whatever, which I decided to associate to this device. And now, if I want to, and if the network works here, because it's a little going back and forth, I can just decide to text my USB armory from my phone using Signal. Let's see if that works. Demo gods. I should have sacrificed more goats to the demo gods. Let's see if we have connectivity. Yes, we do. Okay, so I have a contact here. This is my contact, and I can just decide to open a chat. So I received hello here on my phone. I can do it again so that you can see hello, and then I got another one. And I can also decide to send files directly from here to my phone. So what I can do, I have a file here. I copy the file. I go into my chat, and I send the attachment. And as you can see, I just received a picture of a lovely cat. So you can also, and this of course also works from one USB armory to the other. So what's the takeaway here? The takeaway is that if I want to share a file with a trusted party using the USB armory, I could encrypt the file with GPG, download the file, give it to my mail client, which must have some kind of ugly GPG plugin, and then send an email to my colleague. But with the Signal plugin connectivity, what can I do? If he also has a USB armory which is registered to Signal, or maybe wants it to his mobile phone, we don't care, I can just share the file directly from the domain of the USB armory with end-to-end encryption to him, bypassing all of this. I can just select a file and share it over Signal, going from the USB device itself, which we think it's a pretty cool functionality. And of course, we can also receive files that will just be placed directly into the contacts folder. So I can decide to send a picture back if I want to. So I can just select a picture and then send it. Let's see if it works. No, network is really slow. So when the Wi-Fi goes up and down, this causes problem with Windows. Okay, there we go. You see the notification over there. We receive a message, another message, and then here you see that a file appears. So this is the file that was just sent to my phone to the device. So we think this integration is very interesting, and it makes chatting and sharing files from the device very, very easy. As soon as I log out from the device, the contents are locked, or I can also decide if I want to power off the device from here. I'm not going to do that. I'm just going to log out. As soon as I log out, the partition is encrypted again. And again, this software can also be used not only on the USB Armory, but also on whatever embedded system that you might like. We also made an embedded distribution for interlock, meaning there's a framework called buildroot, which allows you to compile just by using configuration files, which are in the form of with the same standard of the Linux kernel, where you can define what you want in the resulting image. You want glibc, you want SSH, you want Python, whatever you like, and then you can compile a kernel image with an embedded RAM disk to run on a device such as the USB Armory. So we develop configuration that allows easy creation of these kind of images for the USB Armory. So with just 2 commands, it's just easy. This framework would just download and compile everything you need to create a Linux kernel which has an embedded RAM disk with interlock. And why do we do this? We do this because we want the system on a chip to verify the bootloader, and we want the bootloader to verify the kernel image, but not only the Linux kernel, but also the file system which is associated to it. And the interlock application with all of its dependencies can fit in less than 7 megabytes of a file system. So what we do, we put everything in one kernel image, we load that into RAM, and what we have on the micro SD card, either than this single image which is verified by the hardware, it's our encrypted partition. So this is a very minimal setup where we maintain the full chain of trust from the hardware up to the resulting encrypted partition, because this can only be unlocked with your credentials. So this allows to create very compact and very efficient images that they just put in less than half a second on the Armory, and they're very fast, and they only expose the code surface of interlock itself and nothing more. So you can even not have any SSH connection to this if you want to. Now let's talk about the offensive uses for the USB Armory. So as a security tool, as any security tool can be used both for protection but also for attacks. And being in the business of doing security auditing and penetration testing, we also benefit from devices such as this one in our job. So the obvious application of this device is that it provides an easy and powerful means to emulate arbitrary USB devices. And not only emulating them at a descriptor level, which is something which can be easily done with something like the face tensor board, but you can also expose a full driver, which might be already there in the Linux kernel, or that you might want to develop, and also the speed which you can achieve in executing this code is much faster than with other microcontroller-based boards, because you have a full Linux system running on this. You can do passive sniffing. You can do, of course, as I mentioned, DNS hijacking and traffic diversion, because if you expose an Ethernet driver from this device, the host will ask for an IP address, so you can present whatever DNS you want, you can present whatever route you want, and so on. And in fact, we also had a few papers that were nicely done by other groups. One is USB Armory is an offensive attack platform. We have USB devices phoning home, which is a paper about exploring how easily such a device can then exfiltrate data home, and a paper from IBM, which is about transparent defense against USB eavesdropping attack. They use the USB armory for implementing protection, but one of the attacks that they do can also be implemented with the USB armory itself. So in our job of exploring what the device can do in our testing, we found a vulnerability which was kind of hyped because it applied to OS X and iOS. This is CVA 2016-1734, and it concerns the emulation of a malicious Ethernet device. It was found and investigated on OS X, but it also applies to iOS because the same driver code applies to both platforms because there's a lot of code reuse. And this bug was interesting because it worked on a locked session without user intervention. So you would just be able to plug a device on a locked OS X laptop, and it would just trigger the issue. And what made it interesting is that it was announced 24 hours after the FBI confirmed the iPhone unlock, which is very interesting and also gives a lot of trouble and a lot of inquiries because of it. It is, we think it's likely unrelated, but you never know. Now, there's one interesting thing. There was so much journalistic pressure on understanding if this bug was actually used in the FBI case or not, that a week after public disclosure, which is about 4 months after initial reporting, so there was a lot of time to investigate this thing, but a week after public disclosure, because of the very strong journalistic pressures that was there in inquiring whether this bug was used or not in the FBI case, Apple decided to downgrade the impact of the bug from execute arbitrary code with kernel privileges to just a denial of service. And the reason why they did that is because of the interpretation of the panic logs that were sent out. So I think the impact downgrade is debatable, but I'm going to leave that to whoever wants to test this vulnerability, which is why now we're giving details about it for the very first time. So the issue is that a high-speed USB device advertising specific USB descriptors which match full speed values, so not high-speed device, but full speed. So we have a high-speed device which pretends to be a full-speed device, even if it's not, causes OS X to panic and reboot upon specific messages which are sent by the device to the host. So this is fully controlled by the device towards the host. And this corruption, memory corruption, is triggered regardless of the user being logged in or not. And it is triggered by setting the descriptors for the USB endpoint to those values, and then to trigger a very specific payload from the network. So we narrowed down a single IPv6 packet which can trigger this panic when sent from the device to the host. However, this is just a reproducer of the bug. There are many other effects that happens when this scenario takes place, and not always a panic is being triggered. So we think that the panic is being triggered only if we specifically corrupt memory in a manner which is then passes this specific mbuff check, memory buffer check. But in other cases, we will get other results, and sometimes we will not get a panic report or not. Supporting the fact that the memory corruption is more extensive than that specific case. When OS X survives the attack, if you sniff the incoming network packets on the host, you will see that, let's say that you send a ping, a continuous ping to the device, you will see that the payloads for more than one ping gets collected into one giant packet, meaning that we are corrupting the memory buffers, and somehow the host believes that the network packets are much larger than what they are. And also, I would like to point out that memory buffer exploitation with IPv6 on BSD code is something that happened in the past on OpenBSD. So it's a kind of interesting vulnerability, and I would give a second thought on the impact here. Anyway, regardless of the impact, this makes a very good case for the efficiency of using the USB armory in such testing, because we have the ability to easily manipulate descriptors just by changing a few lines of kernel code, and at the same time, we can still present a full valid driver to the host, which is exactly what happened here. Not only we required to manipulate the USB descriptors, but we always had to have a full-blown Ethernet USB driver working, which would allow us to send packets from the device to the host. And this is something which is not easy to do with other USB frameworks. So 5 minutes left for questions, then there's lunch. I think we're doing very well with time. But first of all, I would like to thank you very much for your patience and for your attention. And if you have any questions, please raise your hand. Thank you. Any questions? Yeah.
Hi, thanks for the talk. Is there a possibility to load the PGP key in the secure enclave? So how do you protect the key material?
Right. So there is no persistence on the device other than the diffuse secure boot keys. And there's a symmetric unique key per sock, which cannot be read, which is embedded in the system on a chip. The model for securing user data is that you don't want to be too tied on the hardware features for doing that. So you want to keep all of this data on an encrypted partition, ideally, or on encrypted firmware. And what you do is that you need a combination of two things. You need secure boot to ensure that this specific device can only run your code from the very beginning. And then you need, if you want encryption, which is unattended encryption, okay? You need to use a secret which is stored on the device. If you want to decrypt something with a device which is attended, where you can input data, then you just care about secure boot, because at some point you will have an encrypted partition and you can put your credentials, and you don't want those credentials to be stored on the device itself. If you want this to be unattended, let's say you have an IoT device and you want to have the firmware encrypted and you don't want local attacks to be able to extract that firmware, then you need to do secure boot, and then you need to read the symmetric key from the sock itself. So not from an external memory, which is where the bus can be intercepted on the PCB. And on this sock, there are two ways. Either you fuse your key in the one-time fuses, and you make sure that your code does never allow external debugging to access those fuses, or you use the symmetric key, which is in the system on a chip, which nobody knows. I mean, you can use it, but you cannot know it, which means that when you provision the device, you need to use the actual device that you're going to deploy, which could be seen as a feature or could be very inconvenient. But these are the two ways. We've seen a lot of embedded devices that they just have an external component for doing that. They have like a crypto authenticator, which is external. But the problem with that is that you can always intercept the bus. And if you want to secure that communication, then you need to use a secret which is in the code. And some people, they do secure boot, but they do not encrypt the firmware, and then you can find the secret there. So it's tricky. Interlock intentionally doesn't leverage on this. It only leverages on secure boot because the use case is that you're going to put your password anyway. So we don't want to waste time having secrets which are not necessary. Thank you. That's a very good question. Any other questions? No? Okay. Anytime, approach me if you want, and I can show you the device and ask you questions in person. Thank you. Oh.
Thank you very much. No, just your applause. Thanks.
Thank you.